Well, this problem has, looks like three parts. There's work energy, and then a collision, and then work energy again. So let's see how it goes. We'll start with the motion in the pendulum, right? So in case you've forgotten how pendulums work, we have a pendulum of length L, and it is currently 23 degrees away from the vertical. So this distance here, if this distance is L, and this distance is L cosine 23, and then this little distance here is h, the height through which the pendulum falls as it swings, and then the total length is L, so that means h is equal to L minus L cosine theta, or L minus L cosine 23. For this problem, that works out to be 1.2 times 1 minus cosine 23, which is 0.0954 meters. Now we're going to need that because for a pendulum, you got three forces, right? You got gravity, tension, and your centrifugal force. The work done by tension is zero because the force of tension is everywhere perpendicular to the motion. Tension is radial and the motion is tangential. The work done by the centrifugal force is zero because, again, the centrifugal force is radial and the motion is tangential. And the work done by gravity takes on the form plus or minus mgh. In this case, it's positive mgh because it's going down. So we sum up the works, and we set them equal to the change in kinetic energy. And of course it starts off at 0, and so m cancels out and we're left with the equation v is equal to the square root of 2gh, which is 1.37 meters per second. So that's how fast, at the bottom of its motion, that's the velocity of the pendulum bob. Now at that point it has an elastic collision with object 2. So we're finished with part 1, the pendulum. Now let's consider this collision where the pendulum bob that has swung down has its impact with the mass m2. So here's m1 and here's m2. Now we're told that m1, the mass of the pendulum bob, is mass m, and m2 has a mass 2m. We're not told what that mass is, but we don't need to know. Let's see, it has an elastic collision with mass m2, which is initially at rest. Okay, so we have that v1I is 1.37 meters per second, right? And the final velocity from part 1 is equal to the initial velocity for part 2. And v2I, the initial velocity of mass 2, is 0. This is an elastic collision, and we're only worried about what's going on with m2. So after the collision, v2f is 2m1 over m1 plus m2. I'm using the formula from the formula sheet for elastic collisions, plus blah 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 0. Right, I'm not worried about the second term because v2i is 0. So this equals 2/3, right, because the, well, you know what, it's 2m1 is 2m, and then m1 plus m2 is m plus 2m. Well, that's just 2m over 3m, so that's 2/3 times 1.37, which is 0.911 meters per second. So that's the velocity of mass 2 immediately after the collision. We're going to use that final velocity as our initial velocity for part 3, where it slides across a rough surface with the coefficient of kinetic friction until it comes to rest. So we've got this mass m2, which has some initial velocity v0, and it slides some distance delta s across the surface before coming to rest. So the final velocity is 0, the initial velocity is 0.911. Right? Again, the final velocity for part 2 is the initial velocity for part 3. So to figure out delta S, which is ultimately what we're looking for, We can either use work energy or we can use forces. So either way, we're going to need to know what are the forces acting on this object. So there are three forces acting on the object: normal force, gravity, and kinetic friction. I'll take to the right to be positive, since I've already got initial velocity is positive 0.911. And let's see, so if I do this with forces, then the sum of all x forces is equal to minus mu sub k times the normal force, which is equal to ma. The sum of all y forces is normal force minus m2g is equal to 0. Solving for the normal force, I get it's m2g. I take that and I plug it in back here for the normal force, and I get minus mu sub k times m2g is equal to m2a. The m cancels out, and so that gives me my acceleration, which is minus 0.31 times 9.8. That's minus 3.04 meters per second squared. And then from there, I can use my equations of motion with constant acceleration. Let's see, I know acceleration, and I know v, and I know v naught. So I can use v squared is equal to v naught squared plus 2a delta s. So 0 is equal to 0.911 squared plus 2 times negative 3.04 times delta s. And if I solve that for delta s, I get delta s is equal to 0.14 meters. Now, if I do the same problem with work energy, then I've got to calculate the work done by each of my forces. The normal force does no work. It's perpendicular to the motion. Gravity does no work here. It's perpendicular to the motion, unlike part 1. Kinetic friction, let's see. The force of kinetic friction is mu sub k times the normal force, multiplied by the displacement, times cosine, in this case 180, because kinetic friction points in the opposite direction of the displacement. Let's see, I can rewrite this as minus mu sub k times the normal force times delta s, because cosine 180 is just negative 1. I also know that the normal force is equal to m2g, so I can write mu sub k m2g delta s. Okay, so now the work energy theorem tells me to sum the works done by all my forces and set it equal to the change in kinetic energy. The final kinetic energy is 0, because final velocity is 0. And so I end up with minus mu sub k m2g delta s is equal to minus 1/2 m2 v naught squared. m2 goes away, and so delta s is equal to v naught squared over 2 mu sub k times g, which works out to be 0.14 meters. So either way, you get the same answer.